basically because of geometry, because the BD geometry and the EF geometry in terms of thickness, in terms of length, is exactly the same. Likewise, FAB or AB and EF has the same what? Area. Okay. So now let's look at BD. Okay, let's look at BD. So if we were to focus on section BD now, okay, we're going to focus on section BD. Okay, so we're going to focus on section BD. So I'm going to sketch out section BD. Okay, I'm going to sketch this out. Okay, so this is my section BD. So on this side, on one side is my start. On the other side is my end. Okay, and then this is my Z distance. Okay, so I'm interested now. Okay, the force acting on this area. Okay, I'm interested in that now. Okay, so we know that QBD. Okay, so we know that the Q, not BD but Q BD as a function of Z. Okay, so it will be a function of Z, so it's equal to a y bar, right? So as I said, I like to use the term where you have width multiplied by depth multiplied by y bar. So the width down here that we know is Z, right? So this is our width. We're only interested in the shaded section now, okay? And then the depth, we know that the distance from here to here, that's our T. And the y bar, right? So the y bar relative to the centroid, this distance is 3 inches. Okay, so we multiply by 3. Okay, so now once we get here, we will remove the bracket. This is 3TZ. Okay, so the next stage that we're going to do now, okay, so if we look at the solution procedure, okay, look at the solution procedure, which is in the previous page. Okay, if we look at then after that we have to substitute into this equation now. We have to substitute into this equation now. Okay, so we are going to substitute into that equation. So now we know that shear stress, right? Shear stress along BD, right, as a function of Z. So this is equal to V over I, right? V over I is constant everywhere. Okay, divided by T. Okay, thickness is also constant. So this is equal to 3TZ. Okay. So when we simplify this equation, okay, you can get rid of the what? You can get rid of the thickness. You got V over I multiplied by 3Z. All right. And we know what is our I equal to, right? So V divided by, so our I is equal to 233 over 12, right? So 233 over 12 multiplied by 3Z. Okay. So this will be equal to 3 times 12 divided by 233. So it's equal to 36 over 233. Right? 36 over 233 VZ. Okay, 33 over 233. Right? So now, from here, right, what we're going to do now is we're going to integrate equation number 2. I'll call this equation number 2. Okay, we're going to integrate equation number 2 to find the forces between in between the section BD. Okay, so now FBD is equal, so we're going to integrate the limits is between 0 to 4. Okay, why 0 to 4? Because the distance from here, right, from BD, so this is 0, and the distance to here is 4. So that's why the limits is between 0 to 4. Okay, so 0 to 4. So we're going to incorporate the equation shear BD as a function of Z, and then we're going to multiply T, the thickness, and what is changing is our dz. Okay, so this will be equal to, so we know that V and T are constant. Okay, so I'm going to put the equation in. So 0 to 4, 36 over 233, right? So V Z multiplied by T dz. So what I'm going to do is I'm going to take out V and T because V and T are constant, right? So when we integrate that, we get 36 Z squared divided by 466. Now you guys are better in integration than me. Am I right? You are. You guys are. Okay. So from here, we know that this is equal to VT. Okay. Multiplied by 4 squared times by 36 divided by 466. So it's equal to 288 over 233. That's it. Okay. So this is real simple. You guys say, is that it? Okay. That's it. Okay. Right. So the next thing that we see now. Okay. Before I go on, any question with this? Are we okay? Right. Very simple integration. Okay. Very straightforward integration.
I have a question.
Yes.
I'm just maybe you mentioned this, but I missed it. Why do you keep the thickness as T until the end? Why don't you just turn into 1/8?
Yeah, you can. You
Oh,
want to do that? You can do that also. No problem. Okay.
oh,
The
okay,
answer.
all right, okay,
The answer will be the same. Okay.
got it.
Okay. So now the next thing is this now. Okay. So do we need to find VAB and VEF? Okay. So I'm going to copy this diagram again. Okay. So this is VAB and this is VEG. Okay. So do we need to actually find VAB and VEG? Okay. The answer is no. Okay. So no. Okay, that save us a lot of work. So note. Okay. We do not, or to find the shear center, right? To find the shear center, okay, we are going to take a moment about point C. So where is point C? This is point C. Okay, will be analyzed, right? So what is the problem with VAB and VEG? Anyone? So our next step is to find the what? To find the shear center, right? That is our next thing. But what did I just say? Right? We're going to take moment about what? Point C will be analyzed. So is it necessary to find VAB and VEG? Anyone?
No, because it's on the same axis as
Exactly,
point C.
Anna, you got it. You got it spot on. Okay, we don't need to, is because no need to find. Okay, no need to find. Okay, we no need to find VAB and VEG because these forces will not generate any moment at point C, right? Why? Because moment, right? We know for sure, I'll just write this down. Moment is equal to force multiplied by what? Not any distance, perpendicular distance. And if the perpendicular, so VAB, okay, VAB and VEF, the perpendicular distance is equal to 0, it will not generate any moment at all. Am I right? Right? Okay. So now we are ready to take the moment. Okay, now we are ready to take the moment. Okay, so I'm going to use the next page. Or I need to generate next page. Or I have figure over there. Okay, I will. Now, if I'm changing page too quickly, tell me. Okay, I will. I know some of you are copying this live. Okay, I will slow down. Okay, and I'll let you copy. Okay. So no one is copying now. Everyone is okay. Yes, someone has a question.
Yeah, Eugene.
Yes.
How did you assign FBD to the left and FEF to the right? Because it's not going to be arbitrary anymore when we take the moment.
No, it's not. Okay. So now we know that the vertical, right? The vertical is the control again. Yes or no? Right? So all these points are all the what? Terminal now. Does that make sense? So all these points are just drawn. So all these dots are all our what? Terminals. Okay. So the vertical one's control is flowing down. So all these will want to. So the end. Okay. A simple rule to take is this: anything above the centroid, okay, will go towards the web Q direct or this direction. Okay. Any force below the centroid will disperse itself. Does that make sense? Okay. So this one will contribute to the V, okay, because it's above the centroid. This one is no-brainer. When it's below the centroid, it will move away, right? It will go away from the V at the web. Cole, does that make sense? Is it Cole that asked me that question?
Yeah, sure, that makes sense. I mean, I can remember that rule. Is there a reason why?
Is there a reason why? Let me see. Is there a reason why? It's how the shear flow will be shifting, and I can tell you why. Okay, I can tell you why. If we have a structure in this direction, right, in this direction, and then if we have a vertical, okay, so if this is the centroid, the over here is our centroid. Right, over here is our centroid. Okay, centroid both in the Z and in the Y direction. Okay, so that is our centroid. The force is exactly acting on the centroid. So we know that this thing will twist this way, yes or no? Right, this is going to be the twist. Am I right? Okay, so that's a twist. When there is a twist, right, the shear flow will counter it. So this is our shear flow. Right.
I see where you're going here.
Right.
Yeah.
So that is the shear flow. You know, Cole, you are cheeky sort. I teach this to a professional engineers who are taking masters, and he asking me the question. It's okay, right? So these are the shear flow, right? To counter the what? To counter the rotation. Yes or no? So all this, and if this is centroid, it will counter the rotation. Okay. And I think I have to explain this. Cole, thank you for reminding me. Okay. Then that makes more sense to you guys. Yes or no?
That completely clears it up, actually. That's useful. Thank you.
Okay, good. Okay. Hey, listen. Anyone have any question? Okay, just ask. Okay, don't like.
Yeah. Sorry, Eugene. Quick question.